Hi class, what we've got here is the last couple of slides from our PreCal Math 176 section 9.1. So some of you have already seen this and you got a good start on it. Some of you may want to see it again, or some of you may not have seen these last couple of slides. And your paper doesn't look exactly like this. I spread it out a little bit, put just question 7 on one slide. But we're looking at using other identities to help us do more things. And question number 7 is asking us to solve for cotangent. That's our job. And so we got to find cotangent. Now, I don't have very much information except for 2 facts. Angle T is in quadrant 1. And cosecant of T equals the square root of 17. So this is my given information. And I want to use what I know to help me find something new. And the only way that's going to happen is if I can create an equation or somehow find a connection between what I know and what I want. And that's why it's important to memorize and know a lot of identities, because the more you have in your toolbox, the easier it is to come up with solutions. And here is an identity: cotangent squared theta plus 1 equals cosecant, and that connects the 2 pieces of information in my problem. So I can use this identity for my problem here. Now in the identity it says theta. In our problem it is about t. And I have this part I don't know. I'm going to solve for. But cosecant, I know the answer to cosecant because I was given that value is the square root of 17. Now I'm going to simplify and I'll be able to start solving this. Cotangent of t plus 1. Square root of 17 squared is 17. I'm going to minus 1 on both sides. Cotangent squared of t equals 16. Now, long time ago, some of you may have studied this, some of you may not have studied it. But there's a method called the square root method. And if you have a single second power equation, you can take the square root of both sides. But there's 2 answers. X equals the square root of 49 is 7. But we also know that's not the only answer. Negative 7 times negative 7 is 49, positive 49. So when we do this square root method, we have to remember to account for a positive answer and a negative answer. So we get 2 answers here. I should have made it look better. So we get the positive 7 and the negative 7. Now that is true for us in trigonometry as well. I can take the square root of the cotangent to get rid of the second power. And when I take the square root of the other side, I just have to remember there's 2 solutions. So the square root of the second power will give me cotangent of t by itself equals a plus or minus 4. Now, algebra has given me 2 answers. But now I have to tie it into the geometry. And I've got one more fact, that t is in quadrant 1. And you guys remember A smart trig class? The A means all trig functions equal positive in quadrant 1. So because t is in quadrant 1 here, I have to choose only the positive solution. So cotangent of t equals positive 4, and I'm done. I'm going to throw away the negative answer. The algebra had 2 answers, but in the rest of the context, I only need the positive solution. So here what happened is we used an identity, the identity of the Pythagorean theorem, to come up with an equation that allowed us to solve. Now, you guys have these problems on one page, so I should have told you this before. You kind of have to write small. I moved these problems over to a second slide for me here. Okay, now I want to look at the Pythagorean identities a little bit more. And I want you to be flexible with these identities. You can rearrange them. For instance, number 8. Whenever you see a second power, you should think about, oh, second power, that looks like the Pythagorean identities. And so I see a cosine squared and I see a 1. It makes me think of this one here. Cosine squared plus sine squared equals 1. Now the 1 is by itself on one side. And my number 8 doesn't have the 1 by itself. It has 1 with the cosine. So I'm thinking maybe I could rearrange this Pythagorean identity and find a new variation on it. So cosine squared theta plus sine squared theta equals 1. I'm going to minus the cosine squared theta from the left and from the right, and these cancel out. And I get this new statement, sine squared of theta equals 1 minus cosine squared of theta. This new statement is a variation of the Pythagorean identity. And it tells me, oh, 1 minus cosine is that expression right there. I can use the Pythagorean identity, this new twist on it, as a substitute to simplify this problem. So 1 minus cosine squared is equivalent to sine squared theta. So I just took number 8, this hard problem, and made it a little simpler. Now I have other identities that I can use to simplify the other parts. Cosecant is 1 over sine theta. Now if I multiply the top and multiply the bottom, I have 2 factors of sine on the top and 2 factors of sine on the bottom, which are going to divide down to 1. And in the end, it simplifies to cosine theta. Number 8, that very hard-looking expression has now become much simpler. Moving on to number 9. Number 9, there's second power again. Anytime you should see second power, you should have a little flag go off in your mind. And I want you to think about the Pythagorean identities. Secant squared and 1. Secant squared and 1, that has a secant squared in it. maybe I can use the second Pythagorean identity to help me with number 9. So what I'm going to do is take that identity down here and do a little rearranging on it. 1 plus tangent squared equals secant squared theta. And if I rearrange it, I could maybe minus the 1 over. And if I did that, it's going to look like number 9. I'm going to have tangent squared theta equals secant squared theta minus 1. Hey, this part of the Pythagorean identity looks just like the top of that fraction. So I'm going to use this second variation of the Pythagorean identity here. Oops, sorry. To simplify number 9. So I still have secant squared theta on the bottom, but on the top, I'm going to replace that with tangent squared theta. That came right from the Pythagorean identity. Now I can simplify number 9 even more because I have other identities for tangent. This is squared, and tangent is sine theta over cosine theta. Now secant is squared, but secant is 1 over cosine theta. Now I have a fraction of fractions, so this will be like, I'm going to put the second power on everything now. But dividing by a fraction is like multiplying by the reciprocal. So see how the denominator flipped? Because that's what multiplying by the reciprocal looks like. And I see cosine squared on top divided by cosine squared on the bottom. This is reducible. This divides to 1 and that divides to 1. And so number 9 finally simplifies down to just sine squared theta. That very hard expression in number 9 simplified down to something very simple. This is a very powerful skill that we need to develop using these identities to change hard things into easy things. Last page. There's some other stuff that I want you to be able to do with your trig expressions. For example, 2 sine squared plus sine minus 1. If you look at it hard, it may look like something we've done before. Is that something we can factor? Sure is. We've factored stuff like that a lot. And you guys have gotten pretty good at reverse FOIL. 2x times x. I need a 1 times 1. And to get the signs right, I'm going to have to go minus and a plus. So that's just factoring algebra. Well, you can get a trig expression that sometimes factors as well. Notice this is a quadratic. I'm going to use the reverse FOIL. But instead of 2x times x, I need to get 2 sine squared of theta. So I'm going to do 2 sine theta times sine theta. Now see how that first pair of factors multiply. 2 sine times sine is 2 sine squared. And then 1, I have to get the factors for 1. Well, those are easy. It's 1 times 1. And then I just have to play around this with the signs just like we normally would. And then we can check this by doing the inner and the outer multiplies. This gives me negative sine theta. And this gives me positive 2 sine theta equals 1 sine theta, and that does check with my middle term. So that tells me I got everything factored correctly. Second, number 11. You recognize this, I hope, as something we've done in algebra. 16 minus 9w squared. It's a difference of squares, which factors. We've seen these before. Plus 3w minus 3w. And then we can do the reverse. We can FOIL it out to check and see if it works. Well, that similar kind of factoring can help with trigonometry expressions as well. So this would be 16, it's got to be 4 times 4. 9, it's got to be 3 cosine x. 3 cosine x with 1 plus factor and 1 minus factor. And that is going to multiply out correctly to factor number 11. Number 12. Factor may not be the best word. Maybe we'll want to simplify. So there's a couple of different game plans here. We could factor it, but we don't have anything in common to factor. So I think it would be good if we could simplify this somehow, and having two different trig functions, sine squared and cosine squared, is complicating matters. But we have this Pythagorean identity. Cosine squared x plus sine squared x equals 1. You know, if I want this problem to be only sine, I could minus the cosine. It's not theta, it's x on both sides. And that would give me, oh, I did it like this before. This time I'm going to minus sine squared x on both sides. And this time I have cosine by itself. When I did it before, I had sine by itself. 1 minus sine squared x. This is a variation of the Pythagorean identity. And I'm going to use this to plug in right here. Now it looks like I'm making it harder by plugging this in. But in one sense, it's better. Now I want you to know what I'm doing here. I'm using the Pythagorean identity, and I did make it a little bit harder, but the advantage I gained is my statement is 100% about sine. So now I have like terms, I have things I can simplify, and when I simplify this, oops, I don't want that. When I simplify, I'm going to have 4 sine squared x plus 5 times 1 minus 5 times minus sine. So by doing the substitution of the Pythagorean identity, this whole statement is only about sine. And I can simplify. I have like terms. 4 sine squared and minus 5 sine squared are like terms. So this will equal 5. 4 sine squared minus 5 sine squared is minus 1 sine squared x. So in the end, I was able to take number 12 with some tricky things in the Pythagorean identity and simplify it. So there is a way to factor it, but that's not the most natural thing. I think simplifying it was our best bet on number 12. Hey, I want to encourage you to spend a lot of time practicing and practicing and practicing this 9.1 with the identities. It's a foundational skill. We need it for our equations at the end of chapter 9. And yes, you'll need it a lot in Calculus 1 and Calculus 2. Hey, study hard, and I'll see you guys in class.